faculty and some in SUS undergrads. I did email all the data science linear algebra class to join. So maybe a few of them might be in SUS.
Okay, sure.
Okay, cool. So now we've let everyone in, or are they already in?
I think it's okay. I mean, you can go ahead.
Okay, so everyone's already here. So all right, cool. So good afternoon, guys, and it's a pleasure today to welcome Man Hongying. So Man Hongying is actually a good friend of mine. So he did his PhD in the University of Illinois. Then he went on to do a postdoc at Harvard University, where he really started some of the very first work on variational quantum algorithms. And as you guys know now, back then, I mean, variational quantum algorithms, no one knew what they are. And it's amazing how quickly things have changed in just 10 years' time. Now, variational quantum algorithms is basically one of the biggest fields of study in quantum information, because it's one of the places we can really see potential implementation of algorithms in the near term. And a lot of the first works were started by Man Hong back around about, I guess, 10 years ago now. Time does pass quickly. Since then, well, I first met Man Hong actually when I joined faculty at Tsinghua University at this Institute for Interdisciplinary Information Sciences over there. So me and Man Hong, we were on the same floor, and we were basically about 2-3 office doors apart. And I remember having great conversations with him because he always had this cabinet filled with bottled water. From one of the grants, I think, that you had to spend, and there was lots of bottled water. So I'd always drop by, knock on Man Hong's door, and then Man Hong's like, "Oh, do you have here's a bottle of water," and then we have a quick chat about what's going on. So the Chinese grant money spent wisely on bottled water. I understand it was something to do with meeting supplies, and the only meeting supply that wasn't supplied by the university was bottled water. So we used our grant money on bottled water. So after that, in about 2015, actually, we both got jobs in different places almost at the same time. I stumbled into Man Hong's office. I said, "Oh, I got to tell you something. I got a job somewhere else." And Man Hong was like, "Oh yeah, I got a job somewhere else too." So we basically, I came to Singapore, and Man Hong went to SUSTech, which was a very new university at the time. And it's amazing seeing that university sort of just explode. So since then, since 2016, Man Hong took a faculty position in SUSTech as associate professor, and at the same time, about 1.5 years later, he was also invited to join as chief scientist at Huawei Technologies, where he is at present. So Man Hong is really he's really kind of one of the faces of quantum algorithms in China, and this is a very big. It's got a lot of attention in the Chinese community, where we see a parallel ecosystem to sort of to the Google and IBM and so on in the West. And so Man Hong, we thought it'd be great to invite him over to give an overview of the algorithms ecosystem in China, the opportunities there for those who are interested in going to industry, and then just a general outlook of what is going on over there. Thank you, Man Hong. Stage is yours.
Okay, thank you, Mile, and thank you, David, for the invitation. So I'm really, I'm very happy that I have the opportunity to give a talk again for NTU. And so I would like to apologize that so in this map, actually I skip a lots of details. So where's my pointer? I suppose there should be a pointer, but seems to be maybe here. Yeah, somehow it got changed. So I think so Singapore is kind of a part of the places that actually I got education in quantum information science in general, because I think way back in my PhD time, actually before I joined go to Boston, actually almost I think many summers or holiday, actually I went to Singapore visiting Professor Craig at CQT. So I actually learned a lot during that time. So it's not just only these few points. And I apologize that Singapore probably is not within this map that got cropped somehow. But yeah, so I'm very happy that So I think I got invitation for this colloquium 6 months ago, and then I thought maybe I could come physically and give such a talk, but yeah, currently probably is not so feasible. But anyway, so I'm still very happy that such kind of exchange can still happen. And so today I'm actually going to share some of my thoughts related to the recent developments of quantum computation. So as Amelia also already explained, so I have a kind of a very mixed experience in different areas, and so for each position I kind of shift myself from different discipline. Like from originally I was a physics student, and then I moved to the chemistry department and be a postdoc, and then I moved to Tsinghua, which is related to Prof information. It's actually Institute of triple IS. So interdisciplinary information. Actually, I learned a lot of algorithms and stuff like that. And then now after I moved to Huawei, actually I have to start working more on the software part. So this is kind of a very mixed experience. But actually it seems that I'm going to many places. But I'm very glad that actually I every work I did, actually I worked towards the same goal, basically to build a quantum computer. So now so I feel like now is the time that it's more close to the engineering part. So in one of the recent years, I actually, like, my talk title, I changed it to like quantum software engineering, because I think this is really the part that needs to be done in order to really build a working quantum computer. So this is the reason why, in recent year, my productivity kind of dropped significantly, I would say. So, but I think it's still worth it. So let me so today it's more like a sharing session. So I explain, what is going on and stuff like this. So I think so. You most of the talks in quantum computation, perhaps you always start with the Moore's law, right? Saying that okay, it's going to be the end of the Moore's law. So therefore, we are when we are reached the end, so we are going to the microscopic scale, and where we need to consider quantum mechanics, and therefore we need to do quantum computing. But after joining Huawei, I realized it's not completely true. I mean, quantum computing is a one way to get away from the limitation of Moore's law. But actually, you got a lot of more other choices. For example, you can change the structure. Like you can make it like distributed computing, or even computing in memory, or using other optoelectronic structure, or you can change the material. For example, you can use something like carbon-based semiconductor, or you can consider more exotic two-dimensional materials. So this is another way to go. Or you can change the algorithm. And as we can see that more and more, so people start thinking about, of course, apply neural networks, or even neuromorphic computing. So these algorithms do not need to, you don't need to compute things accurately. You can sacrifice some sort of accuracy in exchange of the efficiency. So there are many ways to go. And so what we have chosen for many years is the quantum computing, which is really a way to change your theory at all. So in the beginning, it's not clear why quantum computing. Like 20 years ago, we just thought this may be the ultimate choice. But so as you realize that now, people talk more about quantum computing, and then is even in the global scales, people are getting more and more interested, and we will see how things go. So maybe to the students. So I would like to explain a little bit about from really a scientific popular science point of view, why what's happening. So why quantum computing in the first place? So if you look at this kind of classical picture of this capacitor basically circuit. So in the classical world, so you describe this voltage or current by counting the number of charges that is got trapped at the surface of the plate, right? So if you increase the voltage, then you get more electron from one side to another side, and then you get more voltage along this across this interface. So the question is, why this electron would not hop from one side to another on the other side. It's very simple because if you apply the classical picture, the electron simply doesn't have enough energy to cross the energy barrier. But for the case of quantum mechanics, if you shrink this scale to a smaller scale, then you start realizing that the particle picture is not true, and you need to consider wave picture, and you got this tunneling. So therefore, if you build a device based on this kind of a classical picture, then on the microscopic scale, you get a very stable structure, but in the microscopic scale, you start realize that you got lots of fluctuation, and this is the so-called the quantum noise. But this quantum noise, the original quantum noise, come from the effect of quantum tunneling. And as we can see that quantum tunneling is intrinsically a physical a feature of our theory instead of the noise. So therefore, the idea of quantum computing is really to turn this noise into something useful. Okay, so so I also would like to show you something that is kind of interesting, because people keep asking what is quantum bits, and how is it different from the classical bits. So here I show you the hardware structure. So for classical bits, basically it's based on semiconductors, so which is a material that is has a moderate conductivity in room temperature. And the interesting point about semiconductors is that you can do different types of dopings. For example, the so-called p-type dopings and n-type dopings. When you put these two semiconductors together, you form a junction. It's called p-n junction. And with this device, you can base on it and build lots of more interesting device and form some logical gates. So, and with this, you can use it. For example, commonly you use some sort of voltage. When the voltage is low, then you say it is 0. When the voltage is high, then you say it's 1. Okay, so this is kind of the simplified classical picture of quantum classical bits. Of course, it's still based on quantum mechanics. So in some sense, the current classical computer, the hardware part is still is quantum mechanical, but the logical part is not. So, but so on the other hand, so for quantum bits, so I take this superconducting bits as example. So you use the materials that is usually is superconducting materials with just for example aluminum, this kind of metal. So at room temperature, this material is a pretty good conductor. But when you decrease the temperature to go beyond the critical temperature, then you have a copper pair forming, and then you get supercurrents, and they becomes very stable. And so if with this kind of a structure you build, you put some barrier. So this is typically a very thin layer of oxide. Then you will see some sort of quantum tunneling. So the electrons becomes a pair, and then this pair of electrons will go back and forth across the boundary. So this is, so if you draw the double well potential sort of, and then you see that, so this the quantum particle, effective quantum particle, go left and right, and at the end you becomes a superposition. So this gives you so basically we turn these quantum effects called quantum tunneling into something useful by designing basically the building blocks from the bottom up. And in the case of quantum mechanics, from the hardware level, usually the logical qubits are represented by the circulations of the currents, for example, clockwise and anti-clockwise represent N0 and 1. So this is kind of the difference between classical bits and quantum bits from a hardware level. And so I actually show some summary, right? So basically the idea of quantum computer is that so the particle picture shows that the system becomes unstable when you go to microscopic scale, and the reason basically comes from the quantum tunneling. And quantum tunneling gives you the ability to build better quantum bits. Okay, so this is the idea, the basic idea of quantum computer. It's very popular science, just to the student who is new to the field. And here I also explain, so just one slide to explain the logic of quantum mechanics. because I suppose some of the students may not be so familiar with this thing. So the discovery of quantum mechanics starts from the black body radiation. Everybody knows about it, and so very quickly, Planck figured out that so if we assume that the materials, underlying material, can only have a discrete energy levels, or can a quantum energy, then you basically can solve the black body radiation problems with only one fitting parameter, which is the Planck constant. So versus the all the classical theory that would fail. So quantum mechanics was or the idea of quantization was immediately accepted. But then this idea of energy discontinuity arises some fundamental problems, because so the idea is that, so if you say the atom, for example, so can only have a discrete energy, then the logical question is how can you change, right? What happens when you change from one state to another? Because quantum mechanics, so you have to make different assumptions if you really want to figure out this thing, because can we accept the fact that physics is discontinuous? So we have snapshot from one state to another state, or we have to consider something that is continuous. So at the end, physicists chose to believe that quantum mechanics or quantum states must change continuously, and this leads to the idea of quantum superposition. So when you change from one atomic state, from one configuration, you change to another configuration, you actually have a smooth transition, but you have to accept another problem that this seems to be contradictory configuration must exist at the same time. Okay, so this is the idea of Schrödinger cat, basically. So I think most of you may already heard of Schrödinger cat already. So this is basically a device that basically amplify the effect of quantum superposition. For example, if you accept the fact that microscopic system can exist simultaneously with a different configuration, you can design a device so that a cat can lead to a superposition of microscopic states. So this is like Schrödinger's thought experiment. And then I think in the beginning, Schrödinger thought it is a bug. So quantum mechanics actually is may not be perfect, but if you expect that quantum mechanics is more fundamental than classical mechanics, then we would need to think about a cat can exist in both states, that is alive and dead. This seems to be contradictory. But after almost 100 years, so nowadays we are actually think that this Schrödinger cat should be true. There's no reason to believe that this cannot be achieved fundamentally. So this is basically I think Schrödinger cat is actually a prototype of a C0 operation. So therefore so in my opinion, Schrödinger is probably the first one who had already this idea of a quantum logical operation. Maybe if we may say Schrödinger already had this quantum idea of quantum computation way back to the very early stage. So but of course, quantum superposition, I already gave up, trying to explain to other people, what quantum superposition is. Actually, I also asked many people in quantum information, it's really difficult, explain what quantum superposition is. And given that even from the physics community, no one actually can, or the whole community cannot reach a consensus. What does it really mean? You can have different so-called interpretations. So we probably would just skip it. So maybe I also skip this. So to just show you, to give you some feeling about the power of quantum bits. Everybody knows it is exponential, but but we really need to have some sort of actual feeling, because especially after I start working on quantum software, and then I have to struggle with with the simulations. So the idea of quantum scaling or quantum bit is that each time if you add each bit then you need to supply like 100% more, right? So double your size of the memory size to store the coefficients between storing the quantum state, even just for the pure state. And I think you know this story, right? So so there was a very smart mathematician who decided, maybe it's just a story, so not true story, right? So I decided this chess game, and then the king asked him, what awards you want to get, and then he said, oh, I just need very few, just need to put one grain of one grains for each chessboard, and then each time you double it, and then very quickly, I think the whole chessboard has only 46 grids, boxes. So basically, so then it actually represents 64 qubits. It's huge, and compare with what we have right now. If you scale up, so if you're in a laptop, if you only have, you can only simulate at most like 20 to 40 qubits, and for the superconductors, usually it can only give you 50 bits. So therefore, if you really want to get this amount of grains, so it will be like maybe the whole country's grain will be taken by the mathematician. Therefore, the story was, the end of the story was that the mathematician was killed. So okay, so I created a kind of a picture or to show that to show you why quantum computing is powerful. So on the left hand side is like a 20 qubit array. So that has been already realized. Something like that has been already realized in the laboratory with trapped ions and also superconducting qubits. And on the right hand side is kind of a 2 to 20 by 2 to 20 size matrix. So what quantum computing is actually does? It does is to with just this kind of a size, if you perform some operation to it, it's equivalent to perform a really huge matrix multiplication. So which means that so with only 20 qubits on the right hand side, it is not the actual mathematical operation multiplication can almost becomes the ability of a classical laptop. So this gives you some idea about the potential. I would say the potential power of quantum computer. So we're talking about 20. I can equally make like 50 qubits, and the physical size will not be much difference. And but the logical size is really huge that I cannot put it on my screen, I suppose. So quantum computation. So many people may not really well, there are different ways to explain quantum computation. So here I choose to have to put it in a rather simplified ways. So for those of you who may not be so familiar with this the concept of quantum computing. So so quantum computation, I think is still based on classical computing, based on 0 and 1. And what you do is so you just exploit the so-called quantum superposition that I just showed, that you have just a few qubits, you have huge different superposition of basis states. You use it for computation. And so the point is that so within such a huge space, you can use very few very economical physical operations, and then you can full quantum parallelism, and then you can apply perform this kind of a big logical operations. And of course, the computation is not completely the same. We actually, the actual computation we usually acts on the so-called wave function, which is like computation of complex values, things like that. And at the end, unfortunately, we cannot extract the information at will. At the end, we need to extract the measurement results kind of randomly. So this is a very different way of thinking about classical computation. So for example, so what you do is like you can for example have some classical function that you want to calculate. You can perform superposition, and then you would just entangle the input and output. And so for this kind of structure, I think so. This is a very popular kind of elementary structure for many algorithms. But even though we have this entangled input and output, you cannot really extract the answer you like, but this structure can tell you something that cannot be easily accessible by classical computer. For example, this if you compare quantum computing and classical computing as a exploring domains, so classical computing can only explore to each path of each time, but quantum computing can explore simultaneously many paths at the same time. But it cannot give you the output. It can give you the structure of the maze. So this is like a very different type of different kind of way of thinking. And as you know, so this it is a very classical kind of or very classical quantum algorithm. So it's the source algorithm that you can use this type of thing to factoring. And although the quantum computer use along this line of thinking has not been built yet, but the fact that the possibility of existence of quantum computer can already in efficient factoring can already pose a threat to the society. This is the reason why we have a post-quantum cryptography, just to try to to avoid the possibility of future the attack of future quantum computer. And actually, many people are now very much actually in reality, because all the information you are sending out, even though you think these are well encrypted over with for example RSA algorithm, but actually many people are now collecting your encrypted information, and maybe in future, maybe 20 years or 30 years or 50, or in future, maybe if anyone has a quantum computer can crack the information. So now we are actually quite dangerous in this sense. And also I think blockchain like Bitcoins, these applications also rely on this kind of encryption, and will also has a potential be attacked by quantum computer in the near future. So then we have to ask, when will quantum computer replace classical computers? And this is a very popular question, and maybe even a question kind of implied by many the media, right? So we are going to have a quantum computer very soon, and everybody, we don't need to use any classical computer in future. But actually, this is not quite true. Okay, so I like in particular to the students, who maybe it could be very misleading, thinking that the future is all quantum. Actually, if you study some even papers or textbooks, it will tell you that in principle, quantum computer can simulate classical computer, and with a polynomial overhead, etc. But actually, this is not, it is true academically, but literally, but in reality, we will, I think, in a very long time, we will not be able to see all quantum structure to be dominated. So I think in the future, the relationship between quantum and classical computer will be very similar to the way plane and vehicles or car will coexist for a very long time. So it's because there are many problems that or many computing tasks. We really need to divide the tasks, so that for the easy tasks, we will just ask the classical computer to do it. For the complicated tasks, for those tasks that cannot be easily be achieved by classical computer, then we will use quantum computer. So just the analogy is very simple, because so we already have a society, built for cars, and then so car is very good actually at turning around and going from one place to another place. That is a relatively not so long distance. You will just drive car. You will not. Of course, you can drive a plane. So you can design a plane so that you can turn around. You can do it, but it's not the way that we're supposed to use a plane. So therefore, this is, I think will be the kind of a reasonable way to think about quantum computer, is to really figure out what are the tasks that will be useful for quantum computer, instead of thinking about we are going to have all quantum. So and also another possible misleading thing is to think that we are going to have a quantum computer very soon, and then we are going to already, or maybe we already have a quantum computer now. So as I think what is happening now is really can be explained by the roadmap of this EU prepared like a couple of years ago. So I think in the beginning at the bottom, when we were all inside university, we were trying to test the whether quantum computation is feasible. We try to do lots of demo and then to check and whether this kind of small scale Schrödinger cat problem is true or not. And then we spend lots of time. And I think according to the roadmap, the first step is to really demonstrate something called quantum supremacy or quantum advantage, whatever you call it. So this, I think in 2019, I think Google already did something, already demonstrate that with a chip, with a superconducting chip of 53 qubits, already such a task can be achieved. Meaning that for the task that Google performed in 2019, no classical computer can perform better than the Google's chip, right? So although there are two caveats. So first of all, the competition is not completely fair because the circuit is kind of tailored to the chips. So it is exactly the kind of things that the chip will be good at. And perhaps another point is that that is actually a sampling task of a random circuit, which is I think it is close to no application. Maybe people have kind of came up with some application, but it's not that practical. You don't have right now we don't really have a classical problem that we really need this chip to solve. Okay, so these are the two caveats. So this is the reason why the next step we need to do is to really get the first star. Okay, to get the first star of showing these kind of chips can solve practical problems. Okay, so this will be the next main goal. Of course, many people say, oh, quantum computing, we have lots of stuff to do, and so with that, you have to build more and more qubits, error correction, whatever, and then so at the end, you want to do a large fault-tolerant quantum computation. This will be the main goal of the whole field. So, but I think it is important that we do our intermediate goals well, so that we can so have a continuous support from the globally to sort out all the difficulties and technological problems associated with building a universal quantum computer. So now if you are too excited about quantum computer, maybe you are not so correct. Maybe it's not okay. But if you think, oh, these are just hype, we are still a long way to go. Maybe it is already underestimated. So therefore, overestimating quantum computation and underestimating quantum computation would not be practical. I would say would not reflect what the reality is going on. I think so. So because in my previous space I compare quantum computing like a plane and car, and actually I show the relationship way back to the year of 100 years ago. So when I think what we have done have seen in the industry is that we really can demonstrate the principle of aircraft. Just this is like what the Wright brothers did. So you can see that. So I also found the same the cars that is gasoline powered car at the same time. Okay, so imagine you are the guys sitting there. You look at the guys flying like this, and so I think this will be like exactly the situation now. Maybe many people were excited, oh, we're going to have a plane soon, or the opposite side will think, oh, it's useless. So what's the big deal? Is you can just sort of in the air for 1 minute. So it's not useful for me to use this car, right? This car will be more useful by the time. So therefore, the point is that I think it is we should be optimistic, but not overestimate or underestimate about quantum computing. And at the moment, as you may already know that, so we are in the region so-called NISQ, so NISQ region, because so if you look at the growth of quantum bits, so we are going to have more and more qubits, and I expect that this year or maybe next year we definitely will hit maybe the 100 qubits limit. It doesn't seem to be a fundamental problem. But still, within the next few years, we are not going. Maybe it is not likely that we can reach the stage of a universal quantum computing where you need to have a loss of qubits to do the error correction. So therefore, it is in order to get the first star that I showed you in the last previous slide, so that we can show something that is practical. So to show some quantum advantage that can relative to practical problems, we may or NISQ may be probably the only way we should look for, because for the fault tolerant case, it's still far away. We still need to build a lot of stuff to make it to solve lots of problems. So in the literature or in the industry, I think three directions that people are looking at, like quantum simulation and quantum combinatorial optimization or quantum machine learning. I think these are the three fields that may be suitable for NISQ applications. And so this is just to show that starting from like 1930s, so we have gone through already a long path from the fundamental to the theory to the engineering. So now I think it is the engineering plays a more and more important role. Let's put it this way. And so for the students, maybe also explain a little bit about the history, a very brief history that with a lot of important details. So about quantum algorithms, I think that the first algorithm that is related to quantum computation is by Deutsch in 1985. The really the algorithm that's shaping the future development of quantum computing. I think it's Deutsch, and it took and by the time it was about 1 qubit, right? One bit function. So trying to show that whether the output is the same or not. So this is related to 1 bit, and it took like 7 years for Deutsch and Georgia to develop the to extend it for for more general cases, for arbitrary number of cases. It took like 7 years, and after 2 years, Shor announced the discovery of his famous factoring algorithm, and also he invented the quantum Fourier transform. And so with that, and then we have kind of quite a lot of progress after that. So we have the phase estimation algorithm. We have for example, we have another growth search algorithm. We also have this Hamiltonian simulation algorithm. And after that, unfortunately, there's no more interesting algorithm. And this is not my opinion. So this is an opinion by Shor. Okay, he wrote in 2003, saying that the title of his article was that why haven't more quantum algorithms been found? Okay, that was 2003, and so these algorithms are more or less became the so-called textbook algorithms. And these algorithms are the common feature about these algorithms is they have they are actually imagined by a mathematician or in a mathematical ways, what the future quantum computer will be. So these are the idea, and okay, so in future, so only after another 6 years, so we have we have this so-called HHL algorithm that is have a more quite influential to the field, and also we have other quantum machine learning algorithms. So here I just pose some example. There are many quantum machine learning algorithms now. I just couldn't figure out which one would be appropriate. And so these algorithms more or less inspired by the development of AI. Okay, so then in the field of quantum computing, we already thinking about applications of like AI, and only a couple of years later, and we have to start thinking about variational algorithms. And I was fortunate enough to be involved in one of these algorithms. So I explain a little bit, why it was a big deal. It was in the beginning, it was not we had a really hard time when we trying to to propose this one, because for VQE everybody knows that there's no big O notation, so all the algorithms before VQE has this scaling. Okay, if you want to claim that okay you are better than classical algorithm, then you must provide a big O notation saying that okay to what extent in the infinite and limit, then you have to show that what are the scaling, and then to show that. So the reason why so VQE algorithm cannot exist before that, because the reason is that because the hardware was not ready. So it's totally it can be published because we demonstrate experimentally the working principle. It seems to work, but we don't have a proof. So therefore, I think the development of quantum algorithm relies on the hardware very much. So if you don't have even before that, if we propose something like this, we cannot get published. So then there are lots of other variational algorithms occurred since 2013. So this is kind of the a very brief history of quantum algorithms. From my point of view, of course, there's lots of interesting algorithms from other mathematical point of views, but yeah, this is like the overall structure situation. And for that, so we can divide. So when we talk about quantum computer, maybe it would be useful for us to really distinguish about ourselves whether we are talking about universal quantum computer or we're talking about dedicated quantum computers, right? So for universal quantum computer, so we have all these the algorithms that is associated with people, last name of the inventors, for example, Shor, Grover, HHL, or maybe Dynamics, we have actually shorter expansion. So so for this type of quantum computer, maybe it takes 10 years or more. There are so many things so many technological problems that we need to overcome. But so therefore, perhaps it is more useful if we consider dedicated quantum computer, so that we forget about error correction, okay, and then we use this variational way of controlling the devices. Actually, so I just name some rather popular algorithms like VQE, QAOA, and QAN for of course you also have quantum annealing for device devices. And in general for these three algorithms, they are actually the same algorithm. In the sense that they are same variational algorithm, variational circuit, for example, and so basically their working principle is very similar. So we try to optimize our control pulses, which may be represented by the Hamiltonian or maybe focus on the quantum circuits. And at the end, we look at our quantum devices, quantum computer as a kind of black box, and then we try to get all the bit strings out. And the quality of these bit strings depends on the quality of this black box. And in general, so we will expect that this quality in general, when your task computing time is long, then your jobs grows and drops. And at the moment, we can be quite confident that we can go beyond classical computing for some period of time. So already, as demonstrated by Google, that for some cases you can do that. And so the idea for universal quantum computation is to extend this line above this dotted line, so that by for example by error corrections, and so to complete a quantum algorithm. And this is very challenging. It's very hard. So the idea of this type of variational algorithm relies on the fact that so we just stop somehow before it drops back. So basically you just when you before you get back, and then you stop, and then you do it over and over again. And this is the idea, I think. So this is the overall idea of most of the variational algorithm for dedicated quantum computation. So and I think this the maturity is very very soon. I think maybe within the 3 to 5 years. Of course, last year or also the same table, I would say 5 years. But as we can see that things are really changing very rapidly, and I get more and more confident that within a few years we are going to show that we are going to be able to show the first practical example of showing quantum supremacy. Okay. Of course, recently we also, in particular, also in China, that we also have something even more dedicated. It's good for quantum simulation already. So I think this within maybe 1 or 2 years, we will see some sort of a quantum analog simulator that can really produce something that go beyond the capability of classical simulation for simulating, for example, Hubble model, things like that. We are going to see this very soon. So therefore, the development of a quantum computation is very divided, I would say. So maybe so due to time limit, maybe I will skip this. So basically, this that is an example how we can make good use of this quantum coherence time by just stopping before the computing quality goes back. So this is like an example of a VQE is like this. And so this is overall idea of what I've been talking about. So if you have many physical good qubits, then we can perform many quantum algorithms with a general quantum computation. And these algorithms usually you have it varies. Sometimes maybe you have a quadratic speed up, or maybe you have exponential speed up, or whatever, something in between. Depends on your number of qubits that you can control. And this algorithm, if you can do it right, you are guaranteed to have a advantage relative to classical computing. But for the case of NISQ, so the algorithms that I mentioned, like VQE, QAOA, and QAN, they are all have potential, but the point is that we don't know. So therefore, I drew these three circles that is across this line. We don't know. So currently you design a VQE algorithm, most likely you are under below this. Okay, you want to simulate molecule, it takes still thousands of cases, and then it's very difficult to really figure out whether you can find some example that's really definitely go beyond this line. So I think it's like a treasure that's hidden under these three boxes that we have to figure out. But of course, my point of view is that now it's not completely in order to get the first star, to show that we have this practical application of quantum chips. So it's not about we need more good quality qubits. We need better hardware. It's more about imagination. It's more about algorithms and software. So this is the reason why I think this is really the most important thing at the moment, is to really get more people to figure out whether we can really show something practical here. I think we may perhaps with these three along these three directions. So I will skip this. I just explained that VQE is kind of the famous name for the literature, but actually at the same time we also published a theory paper that is less known to the experiment, more or less the same time. And so by the time we called it, I didn't create the name of VQE. I create instead the quantum assisted optimization, which seems to be more general than VQE. But at the end, the field chose to adapt the VQE. But actually, all of these algorithms basically are what they are doing is really using quantum chips as a assist optimization. So use quantum states to help you do the optimization better. So this is like the overall idea. So since then so after I moved to Tsinghua, we did the experiments. So this was the first optical, and then trap ion, and then now superconducting qubits. But what I want to say is that after I moved to Huawei, I also try to figure out whether VQE, how large VQE can perform. So even if we have ideal qubits. So we figure out that although we have not published our papers, so I think up to 2019 at least. So I think we could only simulate up to 28 qubits, so 14 spatial orbitals. So I think this more or less is the limit. Although 28 qubits in principle, if you use a better rush station, you can still do the matrix multiplication. But the number of parameters are too many. As you know, there's a problem of a Bayesian plateau. So if you have a deep quantum circuits, then you don't have gradient for optimization. So basically, in our simulation, we can already see such an effect that we need to. So therefore, we need to design better algorithm and then make the length shorter, and so that we can simulate better. So I think this is the biggest problem with a VQE. and that is not so well discussed. Although you can see there many pharmaceutical company, they try to exploit VQE, but I think there are lots of problems if you really apply VQE for drug design, things like that. It's very maybe at the end for drug design or molecular structure, we need a universal computer at the end. So therefore, in order to but of course at the same time we cannot just wait. So we need to build the blocks and make all the building blocks ready. So therefore we have to have to sort out how to build a quantum computer. Basically, I think it is a totally non-trivial task, and and there are many ideas from academia, and we look at the papers, but it seems it may not be practical, because I think many professors in the university have not really get their hands dirty, putting things together. So we have to sort this out ourselves. So we have to focus on basically everything if you want to build a quantum computer. So therefore it's a lot of work. So that's the reason why I couldn't publish too many papers anymore. So Huawei, we actually already took us 3 years making this step by step. So basically now from our side, so I start working with a so-called system called HiQ 1.0. In the beginning, what could I do? So a professor joined a company, with nothing, So then I think that the simplest thing is that, okay, why don't we just do a quantum circuit simulator? Seems to be the very relatively easy. And then we have to also rely on some open source package. So we chose Project Q as our programming framework, and then as a beginning, so we have a really very good structure. And then in 2019, we start thinking about, okay, we need to choose one applications, and then we chose of course VQE is something I'm kind of familiar. So therefore we chose to develop application for VQE. So we develop HiQ fermion, and then also we start thinking about how to improve the pulses. So we develop HiQ pulse. And last year we also cover another possibilities like the combinatorial optimization. So we basically develop a package called HiQ optimizer, and also we feel like we need to also do our quantum circuit better. But we don't. So as Google already have this 53 qubits, we no longer be able to use a simple circuit simulator to do that. So we have to develop tensor network based simulator. So therefore we also developed something we call HiQ Tensor as a package. Now I would say our quantum software structure is kind of complete, or not complete, but it's like a self-contained architecture that can already do many things, interesting things already. So therefore we have keep upgrading our software. But maybe perhaps today I'm running a little bit out of time. Maybe I want to leave my to reserve more time for answering questions, and just to have more discussion. So I will just for the remaining, I will just go very quickly. So I think this is overall, I think among the 3 directions that I mentioned, VQE, QAOA, and machine learning, I think the most promising application would fall into this direction, like QAOA type application, because your at the end, your ground state, your optimized state is just a bit string. So for VQE, your ground state is kind of a superposition of quantum states. So at the end, you just for QAOA, you just need to measure the bit string. So this is much seems to be much robust. Okay, so therefore we have done a lot of optimization to our package so that we can make it support different applications. And we also benchmark our simulator with Alibaba and other works. So I show that we seem to be doing quite well in terms of the simulation capability. And the next step is to find really practical applications. And also we also work on a HiQ Tensor to do better circuit simulation. And so we probably have a paper, so we're writing up a paper to summarize our results. And I think currently we'll be able to simulate the biggest size quantum circuits already. So we will stay tuned, and we will publish a paper for that. And also so other than quantum chemistry, we also want to extend our capability to simulate many-body systems, and we can easily simulate up to 30 qubits, and we compare with literature only 20 qubits. Like I think they may be using some sort of a laptop to simulate. So we are hoping to build the software so that we can help the academia to do better simulation. So this is our goal. And on the other hand, I'm not sure maybe Singapore can also use our Huawei clouds. It depends on our coverage of our cloud service. So we also offer this cloud service, our software. We put it on the cloud, and then we so as a free quantum computing service, and then let user to use our service. And so the advantage of Huawei providing quantum cloud platform is that we have already lots of building blocks available by other business group. So for example, we don't need to develop our own IDE. We have a professional cloud IDE already exists that we can use directly. So, and also we have so this is also accurate. So we also have another kind of scheduler and things like that. So it saves us a lot of time. We don't need to do everything from scratch. So this is why I how I think we have it saves us some time. And in a very recently, Huawei also released something called MISQ, which is like the counterpart of TensorFlow for AI applications. And recently, we also partner with the MISQ team and provide something called MyQuantum. And I think this is already we open source our code already. So this is like a application that can allow people to exploit the interface between quantum machine learning and quantum computing, and application like this. And here I probably will skip that because it's like a very detailed instruction. And way back in China, because in China the number of quantum software engineers are not so many, because in the university no teacher will teach such kind of courses. So therefore, I spend a big deal of time organizing all this competition and hackathon, things like that, to allow students to really know what is quantum computing. And I hope that maybe in the future I can also maybe engage with students in Singapore, also to explore this area as well. I think with that, I think that's pretty much what I prepared. And then so this is the QR code that can lead you to the git.com, which is a GitHub in China. So that you can try our my quantum package that we are happy to provide more and more open source software over the platform. But yes, please if you're interested, you can try to go to this URL. And with that, I think thank you very much for your attention, and I'll be very happy to answer questions and then provide further opinions about different things that you may have about quantum computing in China, maybe, for example. Okay, thank you very much. Am I talking too much?
No, I think it's fine. Mile, you are mute.
Mila, you're muted, yes.
Oops. Yes, great. Thank you for the excellent talk. So I guess anyone in the audience can ask questions. You can use a raise hand icon or just unmute, probably a bit easier. I'm not very good at spotting the raise hand icons. So yep. Someone asks. Okay. For entangled particles, they say that observation destroys the entanglement. If particles can be simultaneously observed, does entanglement still remain? I thought I had, of course, sorry, I can't read. I thought I heard of the possibility of entangled. So basically someone's asking, okay, for entangled particles, people say that observation destroys entanglement. If the particles can be simultaneously observed, does entanglement still remain? as a thought I had was of the possibility of entangled observations, like entanglement, observe entanglement. Can I ask for your thoughts on this?
It's a kind of a very long question. I think it's a very good question, and yeah. So what I described maybe perhaps here with this equation is kind of simplified. Yeah. So yeah, as you know, there are many different types of measurements, and you know what I talk about is like a projective measurement, which is kind of standard measurement. There's also something called weak measurement, and you know POVM and stuff like that. So I mean the answer to the question, maybe if I understand correctly, is may or may not. It depends on how you do it, but usually it does. Usually you will not increase entanglement. You will decrease entanglement in general. So yeah. So I think yeah. I think quantum measurement is you know there's a short answer to it is like there are different ways to do measurement that may or may not preserve entanglement. Actually, there if you consider post-selection, sometimes you may also get more entanglement. Actually, I have to take my statement back.
Okay. Any further questions from the rest of the audience? You can also speak out as well. You don't have to type. No need to be shy. Any other questions? Can
I ask a question, Mile?
Yeah, sure. Go on, Kishore.
Yeah, so thanks a lot. Very nice talk. I would like to hear more about your views regarding why do you think that for problems like QAOA, we expect possible advantage in the near term. I mean, I'm asking this question because problems in QA, they are like NP complete, right? And so when we are, and we don't expect quantum computers to, let's say, like solve the NP complete problems. I mean, so let's say if we have some kind of, let's say, a possibility of quadratic or quartic advantage there, why do you believe that that advantage can be obtained in the NISQ era?
Okay, so I'm trying to understand the problem. So the problem, the question is that why I believe that quantum computer can solve some NP complete problems? Is it
no. So I'm saying that that is not true. Like I mean, quantum computers they cannot solve NP complete problem because the class NP, you know, like and the BQP, like they do not have like I mean, there are problems in NP which are not in BQP. So that makes us think that the quantum computers cannot really solve the NP complete problems, but at least they can give some advantage, like with respect to classical devices. And I mean, I believe that, and most of the community believes that we can have their quadratic or quartic kind of advantage. I'm asking you this question that if, let's say, we have some kind of polynomial advantage there, then why do you believe that in the NISQ era we can have that advantage, like with the like these kind of devices?
Okay, that's a very good question. Yeah, thank you very much for the question. Yeah, so I you know so this you know so the question is why I believe that you know NISQ can really demonstrate quantum advantage, and actually so
no, I'm not asking with respect to like
not every problem, but some problems, right?
I'm asking with respect to NP complete problem. So like for example, BQE I'm not contesting because there you are trying to solve a problem which is QMA hard. So for QMA hard problems, sure, like I mean those problems are much harder. But the problems which are NP complete, why do we believe that for such NP complete problems, quantum computers can give advantage? You know, like I mean, in the near.
Now, okay, thank you for your question. I now understand this much better now. Actually, so recently, I actually learned quite a lot of online courses because of the COVID-19. So I have less time for traveling, and then I can really learn more stuff. And also because I am devoted in QAOA, and I have to learn more about the classical way of solving these kind of NP problems and even NP complete problems. So let me tell you. So even in the classical world, and we don't believe that we have a classical algorithms that can solve NP-complete problems. Actually, but in reality, we have so many quantum classical algorithms solving NP problem. Actually, we have to do it, anyway, because we have to solve it. And I saw a very good video that that solved. I had something similar problem question that you have in mind in the beginning, right? Or lots of NP-complete, big O notation and stuff like that. I saw the video that that really I feel really meaningful. So just imagine I'm looking at a curve like this at the bottom. Or this line, right? So in general, you believe that if we solve some sort of some sort of NP problems, we will at some point we will be going up in the computing time. So sabbatical will be computing time will goes exponential up, and then in the beginning you may say, oh, it's a very difficult problem that we shouldn't solve it. But actually, we spend great deal of time using different type of classical tricks to extend this exponential line to here, so that we can delay, kind of pushing the exponential wall. Okay, so so that we are within a reasonable range, we can solve the problems we want to solve. So you see what I mean? So it's the same thing. So we think that quantum computer is not going to solve NP problems, but maybe for some problems that is within the reasonable scale. For example, I don't know, is 100 big enough? So if you talk about big O notation, is 100 big enough? Is 1000 big enough? No one knows about it, right? So this is the reason why I say, so now it's about imagination or software, or we want to test. You really want to test. It's like an AI industry that you don't expect AI can solve NP problems, but we do a lot of fine tuning of the parameters, and then string structure to make better and better quantum algorithm. I think this is exactly the same situation with classical quantum computation. We need to design a better version of VQE, better version of QAOA, and even better version of QNN, so that maybe we can get some advantage within a range. Within a range, maybe we can solve it. Maybe out of the range, when you get n goes bigger and the algorithm fails. So we are going to have situation like this for a long time. I think this is my opinion.
So basically, you think that can it continue, Mile, or if you want me to we can talk about it offline also.
Yeah. Does anyone else have any questions first? Because just in the interest of time and the other people having a chance to ask some questions. Does someone else have another question? I guess you can ask one more, Kishore.
Okay. So yeah, so basically what you see that, you have your insights are coming from heuristics. Like basically you were saying that, okay, sure, complexity theory wise, because P is not equal to NP, we cannot solve NP complete problems, but we have heuristic set solvers and all, which kind of, seem to do well. And we have many such examples from the classical world. And those intuitions you are carrying to the quantum world and saying that possibly QAOA, we do not have rigorous results, but these heuristics, they might, give us some result in the near term. But I'm kind of skeptic, because the classical devices, they are very good. At the moment, we can run those heuristics and all, because for example, neural networks you can run today, because the devices have really matured. So but if you really think the early days of AI that involve a lot of mathematics, we focus on kernel methods and those kind of things, which were more mathematically mature and all. And over time, as devices mature, you can also run big heuristics like neural networks and all, and see a lot of results. We are in a phase where our devices are not very mature. The quantum devices. So I'm not sure that with the devices that we have, why the heuristic should. Yeah, you see my skepticism, right?
Yeah, sure. It's reasonable to be skeptical, and then and so we are not going to. So the proof that I can potentially give you is, there are two ways I can give you. One is to really use a real chip and show you that, for example, with Google's device. So Google only spent like 200 seconds, and then if you use a classical computer to simulate to the same fidelity, even for like 0.2%, it takes very long time, lots of resource. This will already be some sort of not a proof, but some potential evidence that we can really extract it. So I think that the point is is how it is really the we need to show how we can exploit this kind of structure. So either I give using the real chip, or alternative, that is something what we are doing right now, using quantum simulator, and we look at the scaling, and then try to, based on simulator, we try to design better and better algorithm. And you never know. Don't underestimate the imagination of humankind. So I'm pretty optimistic that so imagine, so just one person in this world, if he can come up with a solution, and then we test it, it works, then it works. So I'm pretty optimistic. It's a very subjective question or subjective answer. Sorry.
I was just thinking, because on different algorithms, you were saying that maybe QAOA is more prominent. So I wanted to know, more about why QAOA and not VQE.
Well, sure. Because at the moment, VQE, many people apply it to solve the molecular structure, that like what we did before. But actually, if you look at the many papers about VQE, actually, these are it may not even be better than the Hartree-Fock solution. So imagine if you just start from Hartree-Fock and then you put some white noise to it, and maybe it is better than the experiment. So this, I think, is a kind of something that is not so well known in the field. And the people thought that, my experiment always can produce an energy surface, but actually they always start with Hartree-Fock, and the Hartree-Fock is kind of very good already. So what you really need to do is not to look at the shape, is really look at whether you can get chemical accuracy. I think this is maybe achieved by Google in 2020, but unfortunately, what they did was use just a more or less a non-interacting electronic system, and so therefore it's still very difficult using VQE, because like what I mentioned, that the final state you want to get is a superposition of quantum state, and you always have the coherence, etc. So for QAOA, it is also a superposition of final states, but at the end you just perform a projective measurement, and then you get a pretty good bit string, and then you can go to another round and another round. So this is why I think QAOA seems to be more robust in this sense. We don't need to worry about so-called chemical accuracy, stuff like that. Yeah.
Thanks.
Great. Cool. I think that's in that case, the last thing I'll just ask you a quick question. This is more on the administrative, I guess, the more industrial side. In terms of if there are students that are interested in going into the industry, in quantum industry, right now, for example, in Huawei, what are the particular skill sets that you're looking for that say someone who's majoring in physics would want to look out for as additionals, rather than your standard physics education with quantum mechanics?
Oh yeah. Thank you very much for the Professor Gu for the this question. So this is first of all, the underlying the bottom line is I think this is really important. You can forget everything I say in the talk, but maybe the title of the talk you need to really pay attention, because I think maybe perhaps in particularly in China, so quantum software engineering is really a big mixing part. Many people say, I want to do quantum computing, and they don't go to the lab and then do all this. But think about it. I mean, in the future, if you really have a quantum computer, we can just compare with classical computer. I think at the end, the hardware part will saturate at some point. There will be people keep doing it. Of course, people keep doing it even for classical industry, right? People also keep doing this hardware chip, but there's huge room available for software part. So therefore, I think this is really missing in I think maybe even globally, right? So we don't have such kind of a curriculum about quantum software. And actually, what is quantum software? And then we don't even know very sure. We're just exploring. So imagine, so Google is the number 14 search engine. So it doesn't matter if you start late. This field is still new, and is many opportunities is around. And for physics students, I would highly recommend them to first of all strengthen their programming capability, and also maybe go to really learn how to build a classical computer, like software architecture engineering, and then you can bring this kind of experience to the area of quantum computing. I think this will still worth it, because if you ask a computer science students to learn quantum, it's very difficult. But if you are physics students and then you learn computer science, I think it is much easier. So I would highly recommend physics students to pay more attention to the computer science part.
Right, great, thanks. Cool. So hopefully we get a quantum software engineering degree here in TU sometime. Okay, thank you very much. I think you said no further questions. Let's thank the speaker, and thanks, Manhong.
Thank you very much. I hope to be able to get in touch with you physically in future.
Absolutely, it'd be great to hopefully have you here physically at some stage.
Yes, thank you very much. Okay.
Thank you. All right, so the colloquium is officially over. Thanks, guys. Take care.
Thank you very much. Okay.
Thanks, David.
Bye-bye. Thank you.
Bye-bye.
Thanks for the talk. Bye-bye.